Hello, everybody. My name is Hector, and I'm an engineer at Airbnb. So here's a brief bio about me. I used to be in the movie industry for about 10 years. So I've worked on things like Shrek and Command and Conquer. Then after that, I went to Google, where I was the tech lead of Google Image Search. And that's a corpus about 1 million times larger than ImageNet, if you're familiar with ImageNet. After that, I decided, self-driving cars are in thing. So I went to the self-driving car team to learn how to do computer vision object detection, like where in the frame is a car or pedestrian. And then I decided to try something new, and I went to YouTube to write the video recommender system. And that's the one where it said, recommended for you, these are your interests. Wrote 4 papers about it, and won a technical Emmy. So now I'm at Airbnb. Just a show of hands, how many people are familiar with Airbnb? Great, that's a lot of people. So Airbnb is this service that connects hosts with guests. And what I'm going to talk about today is not exactly matching the guest to a host, but a tool to help the hosts select the best price for their listing. So when the host goes to Airbnb, they come to this dashboard, this calendar, and then they will see on their dashboard different colored squares for the day. And green is when the price is good and they're likely to get a book. And red is when the price might be too high for the demand and they're not likely to get a book. So this feature lets them select the appropriate price given a bunch of features like demand, listing location, and the quality. So our goal is in this two-sided marketplace, there are 2 sides, right? The guest and the host is to suggest to the guest the appropriate price for the listing. And it's just a tip. They can choose to accept or reject the tip. But this is a human visible model, right? The hosts get to see the prices. So if you're very, very careful with the machine learning, it has to be properly calibrated and interpretable. And so we will divide this talk into 2 parts. The first part is Appraiser, the service that recommends the price tips to the hosts. And the second part I'll talk about is the heavy lifting behind it, which is done by Aerosolve, our open source machine learning project we open sourced last week. And so let me talk about modeling. This is how we cast a problem. How do we set up a problem and how we go about solving it? So our goal is to predict the probability of getting a booking request for a listing. And we have a medium-sized data set. It's about 5 billion data points and millions of derived features. And we have to fit a model to this data set. And what we want to do is to set up the calibrated probability to forecast the probability of book. And in general, there are 3 factors that affect booking. The demand, which is, is there a popular event going on? Is there a high tourist season in San Francisco? Then there's location, the real estate agents like to tell you. And then there's special qualities about the listing, like what's the view like, how many rooms you have. And so let's drill down a little bit into what these features look like. So in Austin, there's a popular festival called South by Southwest. And this is the demand, the nightly rate, historical nightly rate for events like South by Southwest. You can see there's a huge spike, and that spike indicates that there's a lot of demand for listings in the area during South by Southwest. But there are other smaller spikes as well, like City Limits Festival. According to somebody I asked from Austin, it's a music festival. So how do we forecast things like this? We build a model that captures multiple demand features, such as search requests for that date, for example. And this is the output of our model. If we go back 1 slide, you can see it matches the demand pretty well. The other main feature would be listing location. This is a map of the neighborhoods of San Francisco. you can tell it's a very complex decision boundary, right? There's only two features, latitude and longitude, but yet you have to capture such dense detail about your neighborhoods. And we do that with a combination of KD trees and grids. I'll describe them in detail later on. So we have a hierarchical structure to capture not just the listing level, but the neighborhoods, the city level, the country, all the way hierarchically back to the top of the world. And I'll go into more detail in the implementation part. And last of all, we have special properties about the listing. On the top, we have like a houseboat with a view of the Eiffel Tower. And the bottom, a private room that has a view of the Eiffel Tower. They're both, similar in the sense that both in Paris, but they're very different properties, right? One is a houseboat, how often you get to stay in a houseboat. And they have different views of the Eiffel Tower. So we have to take all these features into account, and there are very, very many of them. And how we do it? Well, we built a machine learning system that we call Aerosolve. And you notice in italics it says machine learning for humans. So let me clarify, what does it mean, machine learning for humans? Well, the whole key idea behind this model is to make it interpretable, not just to us, but to the hosts. Because if we tell a host to raise or lower the price, we have to justify the reason for raising or lowering the price to them. So to demonstrate the kind of debuggability our models have, one thing you can ask the model is, where can I find free parking? And then you type it into Spark, filter, where the feature name contains free parking, and then it tells you exactly the latitude, longitude of locations with free parking. Pretty cool, right? You can just query the model and figure out where free parking is anywhere in the world. Another interesting thing is, this is big data. I don't know any Italian. I was debugging the model, and it says Sabbia. It's like, what is Sabbia? So I typed into Google Translate, and it said Sabbia means sand. And then I looked on the map, it's like, it makes sense. This is Playa del Carmen off the coast of Mexico, Mexican Riviera. And right across from Playa del Carmen is the island of Cozumel, wonderful scuba diving. And this is kind of fun, right? You go to work and you want to find all the cool beaches in the world, you just ask the machine learning model, give me all the good beaches in the world. And I don't know Italian, the model just picked it up by itself and told me these are where Italian people are searching for sand. So how do we get around to building such complex models that are also debuggable? Let's talk about non-debuggable models first. So a typical black box model that you find in data science these days would be random forests or neural nets. They are very complex, very deep, and you're not entirely sure the reasons why they say yes or no. You can ask the model, is my listing price too high? And it will say yes or no, or some probability, but you don't know why. And knowing why is really important. Like, for example, our model can say, yes, your listing is priced too high because this is low season. Maybe it's winter in Australia right now and it's cold and people don't travel there. Or you could be a new host with no reviews yet. People tend to like listings with more reviews. So that's another reason, and so on and so forth. We can tell like what amenities people like. For example, people like swimming pools in Bali. And so we want a debuggable glass box model, that's what we call it. And here's how we go about doing it. Suppose we decompose this probability of booking into just 3 features: latitude, longitude, and the price. And we want to calculate the probability of getting a book. And so there are 3 continuous features: lat, long, and price. And this is the location we're evaluating. It's the Metreon. And first of all, we look at what a typical black box model would do. It will make a bunch of splits, like latitude, and then the next split will be puzzling. It's like, why does it split on longitude? Why is it split on price? And then it goes into all the other variables, and soon it becomes undebuggable, deeper than 2 or 3 levels. And you take that one tree and replicate it 1,000 times, and you get this mess that you cannot really debug. And not only that, your probabilities will jump up and down when you change the price slightly. So that's not really debuggable. There's no clear relationship between the variable like changing, like price, and how it behaves. It's just interacting too deeply with all the other features. So what do we do? Now imagine instead of having a random forest, you turn it on its side, and you have very many millions of rules, and only a few of them are activated at any point of time. So if you have like 100 features in your listing, then 100 features will be activated, and any cross features, we call them, like interaction features. And so these are the only features that are activated, and the way we do it is we control the quantization. So instead of branching an arbitrary latitude and longitude, we break the whole world up into multi-scale grids. So you can see that little square there around a metreon, that's the smallest scale grid size. And then there are other ones above them, like the size of the eastern part of San Francisco, then San Francisco itself, then the state of California, and so on. So we take those buckets, we name them as discrete features, like some bucket containing the latitude, longitude, and we also bucket the prices up in a similar multi-scale manner, and then we interact them together. So when you do that, you explicitly do a polynomial expansion on the features, and you control them, so you don't get nonsensical splits like latitude, price, and longitude, and it's all jumbled up. In this ordered way, you can just search through your model as if it's a database and figure out good locations for events, for example. And this is how we actually do it. If you've used MLlib before, or if you listened to the talk this morning, they have feature transforms. We have the similar idea of feature transforms, but these are text files. So you can edit this text file and specify to the model what kind of transforms you want to do. On the top left, we box the listing location into 0.1 by 0.1 latitude boxes, and then it's multi-scale, right? So you can go down to one final level of detail. Then you quantize the price, and then you say interact price and listing and combine them together. And the last transform, the list transform, specifies the order in which these transforms are applied. So you can get arbitrary amount of complexity using this text file config. There's some differences between the way the DataWorks transforms works. In our case, the transform is separated from the model. This is all in Java. And if you wanted to pre-compute ahead of time any listing-specific feature, you could. And we've also optimized it a lot for the use case of one context, like a search query, and multiple items, like thousands of items, like listings. You send them as RPC once, and it does the feature expansion on the server. So your RPC calls are much more compact than if you were to do the expansion ahead of time. So there are several benefits to doing it this way. We write our data once. In our case, we have many terabytes of data. And the transformations are done on the fly, so we don't actually instantiate this expanded feature, because it could be very big. We control the quantization, so you don't have random splits all over the place. It's very orderly and very uniform. We control the interaction, so they're understandable. And they're also very debuggable. Like, I can upload my model to Presto and say, select all the beaches in the world, and it'll just order it. Actually, I have a funny story about that. I was debugging the model once, and it said, Miami Beach, not so good. It's like, that can't be right. Miami Beach is a pretty good beach. And it turns out there's a Miami Beach in Uganda. Who knows, right? It's like, wow, this is cool. I didn't know there was a Miami Beach in Uganda, but now I do. There's also like fun islands I've found. It says HVAR. I don't know how to pronounce it, VAR. But when I search on Wikipedia, it says it's one of the top 10 island destinations off the coast of Croatia. So I love this kind of models because you can debug them, you can figure out what they're doing. And so how do we get nonlinearity? We have a kind of general additive model called additive splines. And there's another story how this spline thing came about, and I'll get into more detail. So this is a very, very dense slide, so let me unpack it. This is the price percentile. Like on the left, the 0 is the lowest price you can have, and of course, in your market, if you're the lowest price listing, you have a very high chance of getting booked. And then 1 is like the highest percentile of being of price in the market, and so very low chance of being booked. So this feature itself is composed of 3 different features, right? The lowest percentile, the highest percentile, and the price itself. So it's already a pretty complex interaction of 3 features. And if you were to use a standard decision tree, it would need like 3 rules just to find the low percentile, another 3 for the high percentile. So that's why we use this kind of continuous models. They're easier to tell the model directly, I want to interact these 3 features in a specific way. The other thing you can do that I borrowed from the generative world was priors. In the generative world, people think, how can I inform my model something I believe in? So generally, I use my intuition to tell the model, okay, I believe ahead of time that lower price listings are more likely to get booked, and higher price listings are less likely to be booked. So I specify a prior ahead of time, and it does 2 things. First of all, it fills in the gaps where there's not enough data. There are higher prices, there are very few listings that cost a lot of money. So you fill in the gap of the data. And secondly, you get rid of a lot of correlated features. So there are other correlated features that just go away when you specify a good prior. Here's another story. You know the jagged line, the black one? That's what happens when you train the prior with the data. The model corrects itself to fit the data. But I was looking at that wiggles, I was thinking, that's not very good. If I'm a host of Airbnb and I change my price, I don't want the price to jump up. It's like, yes, good chance of being booked. No, yes, no, yes, no. So here's where the story comes around. Remember I said I used to work in the movie industry. Well, I was also an artist for 6 months. And one of the things I did was the foot splashes for the movie Madagascar. You have this giraffe dancing around on the beach, and every time it hit the ground, there's this fountain of particles, the sand splashes, it goes whoosh, and then it slowly settles down. So how do they do this movie magic? It's not by physics. There's no physics in it. It's usually controlled by these things called splines. And splines are these smooth curves that smooth out all these wiggles by approximating them with polynomials. And to model this polynomials, I choose the cubic Bezier curves. That's like a cubic polynomial, but with much better numerical stability. Instead of doing it as 1 plus x squared plus x cubed, the normal way people do, I instead use a Bernstein polynomial. That's a different polynomial space. It's more numerically stable if you do SGD, because these are the 4 control points. If you use Photoshop or any kind of animation package, you have 4 different control points, and you move them up and down. So I was thinking, great, I know this from computer graphics, let's apply it to machine learning. But I found this very weird thing. It's like the endpoints don't usually match up. And so what do? I just add 2 direct deltas at either end. A direct delta is like a spike function from physics. Is when you do a FFT of a sine wave, you get a direct delta. So that's what it is. This particular one that looks so strange is the day of week feature. So 0 is Saturday, and 6 is Sunday. So you can tell there are 2 spikes. The weekends are good for us. That's when most of our travel occurs. So we have 2 spikes to model that situation. But during a week, it's more increases gradually, like a smooth curve. So we project that to the Bezier cubic function. And the debuggability of this model is fantastic. I can show the interaction of 2 features. In the red, we have just the number of reviews. So you can see if you have no reviews, that's not a very good thing, because the most guests want at least one review. But the moment you have one review, suddenly your score jumps up. Probability of getting booked is higher. On the other hand, 3-star reviews on Airbnb are not so good. So Airbnb rates, guests can rate hosts from 1 to 5. But like most rating systems, people peak around 3, 4, or 5. Like this morning, you saw they use 4 and 5. 4 is not so good, and 5 is good. Similar for us, 3 is not so good. And you can see the effect, right? That's in the yellow curve. Like having no 3-star reviews is good. But when you have 1 is bad. But that's where the interesting thing happens. You can see it curve up at about 12 reviews. The effect goes away. That's because there are lots. Once you have lots of reviews, the fraction of reviews that are 3-star drops, and the effect of it goes away. So that's very interesting. You can see immediately, just by plotting the weights of the model versus the feature value, how your variables interact. And that gives you a lot of insight. The equivalent decision tree model will have 2 times 3 branches, or 6 branches at least, interacting with all sorts of other weird features, and it's difficult to interpret. So that's why I'm such a proponent of glass box models. You can actually see the interactions between variables. And this is very nonlinear, right? It's not a linear interaction. It's a very nonlinear interaction. So when you have very complex models, they can cheat. You see the wibbly wobbliness of this? That's not good. This is some kind of count feature where the more of it is generally better. And in the top part, the green part, that's what I expected. But the red part is not what I expected. Why are there fractional values in the first place? And why are the fractional values negative? Turns out that the model had exploited some future information. That's the tricky part about forecasting. It's not just training and holdout. It's also how much future forecasting ability do you have. So one example could be search ranking position. If you ever put that in a search model as an explain away term, it's great, and you find it in your training and holdout, but you don't find it at scoring time. So this is one of those weird features. And with debuggable models, you could just run a monotonicity filter, just find every single spline that is wiggling like that and detect them, and use that to debug upstream data flows that are buggy. Because frankly speaking, in the real world, you have no control over buggy features. We have weird listings with 1 million bathrooms. I don't know where it is, but I like to see it. And other things like that, you have no control over because maybe the data comes from the host. So having a debuggable model lets you automatically find bad features like this. In a neural network or a random forest, you'll just exploit this feature, and you will never know that your features are bad. So some math things. How many people here are data scientists? Okay, about a third. Well, the people who are not, please bear with me. It's regularizing these models are difficult. If you use your standard L1 regularization, it tends to pick up noise. For example, the multi-scale grid I talked about, it'll pick up the smallest neighborhood region around a listing. And that's not so good. It doesn't generalize very well. If you have a new listing, and maybe it's a neighbor, somebody new that doesn't happen in your find tile, you lose the back-off capability of a multi-scale pyramid. So I mix L1 and L2. But that doesn't regularize enough too. For these really high capacity models, I borrowed some tricks from the neural net community, like dropout. There's this amazing thing that we discovered that if you randomly delete 20% of your features at training time, your model gets better. And the reason why it does that is it sort of trains all these features independently of each other. And so it doesn't get dependent on some other feature. So it's almost like random bagging. We also do bagging to reduce bias. But that's for a linear model. For a spline and continuous spline, if you did L1 regularization, you just drop holes in it. It's not smooth anymore. If you did L2 regularization, you're shifting the whole spline down. So anything that's spiky, like my reviews, get penalized unfairly, because honestly, a spline is only evaluated at one position at any time. So it does not make sense to do L1 or L2 weight regularization, but instead we do the L infinity norm regularization of the group. The group meaning all the spline knots, we scale it down so that it doesn't exceed some level. So there's a bunch of miscellaneous stuff that are pretty cool that don't really fit with the rest of the slides, so let me go over some of them. This is what our stack looks like. Our front end is in Ruby. It gets a request from the host. Then we have a bunch of Java servers that at runtime scores the requests. That's written in Java, so the feature transforms and the model inference are done in Java. And the reason is you want your scoring servers to be as lightweight as possible. A lot of engineers might not want to learn Scala, so we separate it out as a module by itself that they can include in their server. And on the back end, we have machine learning in Scala. That's what the Databricks and Spark people love. So we do the training in Scala, and it runs on top of Hive and Mesos. Our data is stored on Hive, so we do Spark SQL, and it's distributed all over using the Mesos container application. This is some comparisons on different kinds of models we tried. We've tried a max out with about 500,000 parameters. Max out is a neural net kind of model. We've also tried boosted stumps. Boosted stumps are very compact. They're like one-level trees. But the models that came out of it were undecipherable. There's a lot of price greater than 10, price greater than 10.2, a lot of splits like that didn't make much sense. Then the linear product quantization model, that's the one that I alluded to early on, but it's sort of like a discrete model. You get a lot of steps, but we wanted smoothness, so we ended up with a spline model, which has about 500,000 parameters. It starts out about 30 million parameters, and after training, it reduces in size to about 500,000 parameters. And you can see the performance increasing. Most of that is because we can debug the model. We can figure out where it's deficient. And the way we do it is looking at extrema. If we're doing a regression model, we figure out where it disagrees most with the prediction. And then we debug that feature and figure out, for example, if it's a new host, we don't know anything about them, maybe it's time to add an image content feature. And I'll talk more about that. For geographic modeling, we built a special kind of KD tree. You notice it doesn't split across the water boundary. Our first initial KD tree would split on the median, but that's not so good because you want to keep clusters of listings together. So we instead used that formula to construct a KD tree that kept neighborhoods together. And finally, like I mentioned, we have some image analysis. On the left, we have the ranking order trained by professional photographers. They tend to like ornate living rooms and very brightly lit living rooms. But the guests themselves, on the other hand, exhibit different behavior. They tend to like warmer colors, warm bedrooms, comfortable spaces. So we just use both. And they're just two different scores that the model above can use however it wants. And finally, just to demonstrate that machine learning is equivalent to compression, this is one of the demo programs in Aerosolve. It can be used for more than pricing. So winter is coming, right? And after winter, there's spring. I promise somebody will say a Game of Thrones reference. So I took some pictures of a crocus, and then I trained a model that predicted the color given just the X and Y location. So for every pixel, I'll say, what's my color given 0, 0? What's my color given 0, 1? Just run through it, and then limit the capacity of the model. So from like 100x compression, the first thing it learns is all the twigs. Then it learns the white leaves. Then it learns the blue flowers, and then finally the green leaves. at about 10x compression. So machine learning is the same as compression. There's no difference between generative and discriminative models. And any more questions?
So we're going to have to, my mic's on. So we've only got time for about 2 questions. So we'll do one right here.
Yeah, I guess I would think one of the big predictors of pricing and booking at Airbnb should be competitive pricing of hotels and things like that. How often can you update your systems so that, I mean, can you do this on a daily basis to have
Yes,
a good prediction?
we actually update it every day. The models are scored every day.
Okay, one more question. And if you're on your way out, please do so quietly. Last question here.
How do you monitor the accuracy of your models? Do you have an automated process which detects if you've got some interacting features?
Right. We have several checks, data checks. If they violate any known conditions, we fail the model. If the model doesn't pass the holdout AUC at a certain threshold, we fail it. And if any of the sliced metrics, we slice it by very many variables. If any of them fail, we just discard the model and use the previous days.
All right, thanks very much.
Thank you.